So the last topic that we will cover for calculus are functions of many variables. So in all the previous sections, when we studied integrals, we studied derivatives, and we studied maxima and minima, we were dealing with functions that were more or less from R to R. The domain could be, for example, some subset of R, but we were always interested in functions where I have a variable x, which is mapped to some numbers. Okay, so for example, we had x squared, the logarithm of x, and so on. But similarly, we can also think of functions that map not only just one variable x, but multiple variables to some number which takes values in R. Let's think of an example. I mean, very simple. And although this would be an example not of a real functions, but of an integer function, that this is just to give you all an idea of situations where we might be interested in more than one variable. Suppose you're interested in how the number of items produced by your business, as well as the number of employees you have, how those affect your profit. So suppose that you have some functions, like a function that maps the number of items you produced as well as the number of employees you have to some number that describe your profit. Now, of course, as I was saying, this is not a real function, it's an integer function because the number of items or number of employees are integers. But here you are interested in seeing how these two variables together, number of employees and number of items produced, map to profit, so to a unique number. Similarly, there are many situations where we are interested in this type of problems, but we have real numbers instead of integers. And this is what we will study today. So, for this type of functions, where I have many variables, x is now a vector that takes values in r to the n, meaning r times r times r. So I have, say, for example, x1, x2, x3, xn, and each of these take values in r. Okay? So we denote usually vectors with a bold, so I have a bold x, which stands for x1, x2, x3 up to xn. Now in some situations where it's simple, for example, if I have 2 or 3 dimensions, 2 or 3 variables, then I may use equally x, y, and z. We may in practice be particularly interested in functions with just 2 variables, since we are still able to draw the variable. Now, instead of being in 2 dimensions, it's going to be a 3D plot, where I have x and y, and then on the z-axis I have a surface that depicts the function as x and y value. But we will not, of course, we will not draw this by ourselves. It's just to have an intuition of when these type of functions may be useful. Now, the first thing that we did when we were working with real functions in just one variable was to find the domain of these functions. And we saw that rules that may be used are that the denominator must be different from 0, the argument of the log must be larger than 0, and the argument of a square root must be bigger or equal to 0. The exact same reasoning follows for functions of many variables. So here, for example, let's just look at the first example. I have a fraction where I have x squared plus y cubed divided by y minus x plus 2. Now, x and y here are variables, are things that I'm studying, and what I want is that the denominator is not 0. So what I must have is that y minus x plus 2 is different from 0. So in this case, the domain cannot be r squared, it must be some subset of it, because y and x cannot take values in r. I must have that y minus x plus 2 is different from 0. So the domain will be all a subset of r squared minus sort of y minus x plus 2. Here I don't want to be very precise, I just want you to get the intuition behind it. So now I have a function of many variables, and when we had a function of one variable, we computed derivatives. Now we can do something very similar with functions of many variables. But now, for example, both x and y are variables. I can take the derivative with respect to x, and I can take the derivative with respect to y. Now, in this case, a derivative is called a partial derivative because I can take it with respect to a specific variable. And it's the derivative of the function f computed over the variable I'm interested in. And the same exact rules follows as in the one single variable case. The other variables are considered constant. So the simplest way to illustrate this is through an example. Suppose I have a function f of three variables, x squared plus 3z minus 2y to the 4. So here I have three variables that are known and that can vary. So what I can do is to compute the derivative with respect to x, the derivative with respect to z, and the derivative with respect to y. So when I do that, for example, let's suppose that I compute the derivative with respect to x. Then here, whatever is not x is considered as constant. And x is the only variable that I consider as unknown. So what I would do is compute the derivative with respect to x of these. 3z and 2y to the 4 are constant, and therefore the derivative is 0. These are cancelled. The only thing that I compute the derivative of is x squared, and the derivative with respect to x of x squared is 2x's. Suppose I take the derivative with respect to y. Then x and z are constant. And I compute the derivative of minus 2y to the 4, which is minus 8y to the 3. Similarly with z, x and y are constant, and the derivative of 3z with respect to z is 3. Let's look at another example. Here I have a function of two variables, x and y, and I have that the function is x squared e to the sine of y. Suppose that I take the derivative with respect to x. Now, e to the sine of y is considered constant. So this is a constant that multiplies x squared, so I know that the derivative is equal to the constant times the derivative of x squared. So it's e to the sine of y times 2x's. On the other hand, if I compute the derivative with respect to y, then what I have is that x squared is constant that multiplies something which is unknown, my y. So x squared stays, and then I compute the derivative of e to the sine of y, that applying the rule for composition of functions can be shown to be equal to e to the sine of y times cosine of y. But this doesn't matter, the details of how I computed this derivative. So now I have a vector. Well, what I have are many partial derivatives with respect to any of the variables of my problem. I can store them in a vector, and that vector is actually as a name and is called the gradient. The gradient is the vector where I store all the partial derivatives. All derivatives with respect to each variable of my problem. So if, for example, I have a function of x and y, the gradient is going to be a vector with two entries, the partial derivative with respect to x and the partial derivative with respect to y. The following step that we did in order when we were studying functions of one variable was, okay, we computed the first derivative and then we set it up equal to 0 to find maximum and minimum. And actually the points that for which the derivative was equal to 0 were what we called a critical point. We can do the exact same thing for functions of multiple variables. So now I can set the gradient equal to 0. And now this is actually a system of equations. It's not just an equation. Let's look at an example. I'm not going through the details, but I just want to show you. So suppose that I have a function here of three variables, x squared minus 2y times x minus 4z squared plus 8z. I suggest you to go through the steps that I did to compute the partial derivatives so that you actually get a better understanding, and then setting the gradient equal to 0 is equal to setting up a system of equations. So the partial derivative with respect to x can be shown to be 2x minus 2y, and I set that equal to 0. The partial derivative with respect to y is minus 2x, and I set that equal to 0. The partial derivative with respect to z can be shown to be minus 8 times z plus 8, and I set that equal to 0. Now I can solve this system of equation using any method that you like, and one can show that the solution is x and y equal to 0 and z equal to 1. So the point 0, 0, 1 is the only critical point. Okay, so critical points for functions of one variable were found by solving the equation that the derivative is equal to 0. Similarly, for functions of many variables, critical points are found by solving the system of equations, which is found by setting the gradient equal to 0. So these critical points are just as for functions of one variable used to find maxima and minima. So maxima and minima are critical points, and there are critical points that are not maxima, global maxima, global minima. So the results here are exactly the same as for functions of one variable. Now the idea is that well, finding whether a point is a maxima or a minima is actually a global maxima or a global minima or a local maxima or a local minima is actually tricky. And we will not develop a method to actually find it. So for functions of one variable, what we did was we computed the second derivative and we checked the sign of the second derivative. Now, the same thing doesn't exist really for functions of many variables. We can still compute the second derivative. But now, well, there is an issue. There is an issue. So when we had just function of one variable, we computed the first derivative and then we computed the second derivative. Now, though, we can mix things up. So, for example, I have a function of x and y. I can compute the derivative with respect to x, and then I can also, again, compute the derivative with respect to x. But equally, I could compute first the derivative with respect to x, and then the derivative with respect to y. Or I could do first y and then x, or I could do y and then again y. So I have many derivatives of order 2. And what we do is actually that we store them in what we call the Asian matrix. So beforehand, let's give a simple example. Again, I'm not going to go through the details, but I just want to show you. So I have a function of x and y, which is cosine of x times y plus y squared. I can compute the partial derivatives. I can compute the derivative with respect to x, and with a little bit of effort you can find out that it's minus y sine of x times y. And I can compute the derivative with respect to y, which takes this expression. Now I can compute the derivatives of these, which would be a second derivative. But I can compute the derivative with respect to x of the partial derivative with respect to x, which would be this object here. I could compute the derivative with respect to y of the partial derivative with respect to x, which would be this object here. I can compute the derivative with respect to y of the partial derivative with respect to y, which would be this object here. And again, I can compute the partial derivative with respect to x of the partial derivative with respect to y, which would be this last object here. So I have a function of two variables. There are two partial derivatives of order 1, and then there are four partial derivatives of order 2. And one thing that we can notice is that actually two of these are equal, and this is not by chance. So this is what is called Schwarz theorem, which tells us that under some conditions that for us are actually always met, if I compute the second derivative and I first compute the derivative with respect to xi and then with respect to xj, it is actually the same as computing the first derivative with respect to xj and then with respect to xi. So this is what the theorem tells us. So here, this was an example of the theorem. I computed the derivative with respect to x and then with respect to y, or I computed the derivative with respect to y and then with respect to x, and I actually get the exact same thing. So we have all these objects, all these partial derivatives of order 2, and what we can do is that we can store them in a matrix that we call the Asian matrix. So it's a matrix where in position ij, I put the derivative of second order, where first I differentiate with respect to I, xi, and then I differentiate with respect to xj. So the theorem tells us that since if I differentiate with respect to x and then xi and then with respect to xj, or if I do xj and then xi, since this is exactly the same, the matrix H is symmetric. Now, just to connect some ideas with that we developed in linear algebra with calculus, well, as I said, for functions of multiple variables, we cannot determine if a critical point is maximum or minimum very easily. For functions of one variables, we just had to look at the sign of the second derivative. Whilst here, it's a lot more complicated, and actually, it's the eigenvalues of this matrix that tell us something about whether critical points are maximum or minimum, but we will not study any detail of this whatsoever, okay? It's just to give you a reference. So in the lecture notes, there is also an example that I go step by step as to how I compute the first partial derivatives, and then I find the critical points, and then well, I still find the critical points, and I think in the lecture notes then there is also how I compute the Asian matrix. So this is basically all the material for calculus. If you have any doubts or you want any clarifications on things, we can look at them tomorrow